Hello guys, this is my first video regarding my dissertation. In this video I'll try to explain what my dissertation is all about, the challenge that will be in the path of my success, and try to explain some ideas that I had in order to succeed in my goal. As I said, this is my first video in English, so I hope you understand my English, and I hope it will get better in the future. So let's get it started. Okay, my thesis is about sensor data integration, inertial sensors data integration, and image acquisition in order to balance statically a humanoid robot. What I mean for static balance is the ability to recognize and counteract external perturbations in the system. Take a look at these rocks for example. If they were to be the representation of my humanoid robot, then if I apply a force here, what will happen is that the rocks on the left will probably fall, because there were some perturbations in the balance, in the global balance of the system. My purpose is to develop an algorithm that will counteract this force that I made. So the real question here is, how will the image acquisition and the data provenient from the inertial sensors gonna help me develop this algorithm? I may have come to a conclusion that maybe will not make my mentor be on the bright side, because I came to this conclusion: if blind people can walk, maybe our vision, even though it is important to our balance, is not critical. Maybe what I can do is recreate synesthesia and the vestibular system just with the inertial sensors, and this is how I plan to do it. What I'll need to do in the first place is to disassemble the robot and measure each rigid segment. Then I will weight the segment and try to calculate this center of mass, as we can see in the figure. The beauty of this process is that I can measure the different properties of the different segments and store them in a header file where I can change them if the need comes to. This will also give me the possibility that if I have a very successful algorithm, and then it will be very easy to implement these algorithms in all the robots, because all you have to do is change the macro. Before we go on, there is an important thing that I need to clarify. The most two important data that we'll recover from the sensor is the measure of forces in XYZ, as well as the angular speed of XYZ as well. This will allow us to know which forces are actuating where, and what is the speed and location of the sensor in a given coordinate of time. If we assume that the gravity has a normal axis to the ground, then we can say that the overall axis of the robot is collinear with the axis of gravity. So if we can sense the forces that are actuating on a sensor, it is theoretically possible to know the orientation of them in space. Now that we can position the segments in space, it is easier for us to calculate the distance between center of masses and also the angle made between them. The next step is to test the robot and set the values that are within the possibilities of movements of the robot. What I mean is, for instance, the knee can turn from let's say 0 degrees until minus 90 degrees, and this will give us the possible positions of the knee. Okay, this concludes step number 1. Keep in mind what I've just said about the possible positions of the robot, because I will be bringing this theme up in a few minutes. Well, welcome to step number 2. In this step we'll try to balance the robot. In this case is showing a not statical position, but for a statical position it is a easier thing to be done. Okay, the first thing we need to do is know what is the relative position of all the segments in the robot. After knowing the relative position of them all, it is important to know the relative position of each center of mass that is within the robot. After knowing this, it is the simplest thing to do to calculate the overall center of mass of the robot. Knowing the overall center of mass of the robot, it is important to know where the overall center of mass of the robot should be in order for the robot to balance itself. And then all we have to do is try to move each segment in the best way possible to make the overall center of mass of the robot and the area where it should exist one and the same. So this is where the thing gets tricky, so I'll try to simplify it as much as I can. But it isn't possible for the robot to make certain moves, even though those moves would balance back the center of mass to the desired location. For instance, I cannot have the left leg and the left feet disattached. They have to be attached. So I guess that the tricky part of this programmation is to make an algorithm that will look for the best position of each segment, and also that this given position is possible and will achieve the purpose of the robot. I believe that the first problem is about the calibration and the data input of the sensors, because the calibration must be correct in order for the correct data to be read. And also we need to know exactly, or in this case I need to know exactly, what the values coming from the sensor actually mean. The second problem of this program is that if it runs 30 times a second, it will probably prevent the robot from moving, because when moving, the balance point of the robot will be disturbed. So I'll have to make the adjustments for this particular case. The third problem that it can possibly occur is that the sensors will not be aligned with the center, the mass center of each segment. So it is quite possible that the mathematics needed for this to solve these problems, to solve these cases, will be very complicated. So this is definitely a problem. As you may remember, my thesis title is the integration of inertial sensor data and visual systems in the head of the balance of a human robot. So you must be asking by now, hey, where the hell are the cameras? Have you heard of ego motion? Ego motion is basically the usage of two 2D cameras or one 3D camera in order to know the position of this given camera in space. Say that we have two cameras in the top of a robot head, and the camera A is recording perspective A and camera B is recording perspective B. Inside the program, inside the robot, there is a program that will compare the perspective A and the perspective B, and will measure the distance between points in both images in order to create a 3D world. After recognizing this 3D world, it's relatively easy to position the head of the robot in a given position relative to the other points that were measured by the cameras. And knowing the position of the head, it is very easy. Knowing using the inertial sensors, knowing the relative positions of all the segments, So now we have a balancing robot that knows his surroundings, knows where he is, and also can interact directly with the world. Thank you guys for watching. Any doubts you can comment. I'll try to respond as soon as I can. Thank you.